leaderboard for each of the projects are set up. But my TAs have told me that there is too many people on, so I have a sort of an imbalance on the people working on different data sets. So what I would like is to have sort of balance. So what I'm going to do is we're going to try to figure out a way to move some of these people to work on other tasks, and we'll figure that out. Okay. Okay. There was some confusion with problem 4 of the homework. I've made that number 4 was the problem that I made, and I made lots of typos and here and there, and I needed to figure out whether that's the CELO code actually worked or not. And I verified that the pseudocode really works. Okay. And what is it due? Is it due today? No. So I tried to answer all the questions that was sent to me. But I hope it's okay. Any questions before we go? We'll probably have one more homework set. I think, let's see. It's this week, next week, and probably 2.5 weeks. So 4 or 5 lectures. Including this one, maybe 6 lectures. And we'll be sort of done. And I don't think 6 lectures will be enough to cover all that I've planned to do, but I'll try to do my best. Okay. So there's sort of a change in the syllabus. We'll modify this, and please give me your feedback. Tell me what you like and what you don't like, and what you like, the final 2.5 weeks to be. Okay, so we're going to look at, I was away last Friday, and the TAs went over backprop, convolution, talked about pooling, and some, was it PyTorch? Programming framework for doing deep learning. Okay? And today I'm going to talk about a couple of architectures that have made impact. Okay. So I would like to look at some of the tasks that people have been working on. So on the left-hand side, from your left-hand side, there's this task. Given an image, and you want to label what's the object in the image. Okay. So here is a cat. Okay. This is a single object in the image. You may have many objects in the image, and that will correspond to multi-classification. Okay. Then there is this task of classification and localization. Where is the cat? Okay. So there's a red box, and what's inside that box? Okay. So that's cat, and it's located here. Object detection is location of the objects that you've predefined. So I'm going to say 200 objects. You did define 200 objects. You know, cat, dog, duck. Will be the objects. And given an image, you want to find the location of these images. So this is called object detection. This is classification. This is classification and localization. And then there's this task of instance segmentation. Okay. Instance segmentation is putting a label on each of the pixels. Okay. So for each pixel, oh, this is an object that we are looking at, we want to find, and it's a dog. So for each pixel, you put a label. And here in the object detection, you place a box on the object. In instance segmentation, you put a label on each of the pixels so you get a really fine outline of the objects. Here it is, dog, and there are 2 cats. Okay, and each of the cat would have a different sort of boundary. So this is cat 1, and this will be cat 2. Okay. And then that will be duck. Okay. So this is instance segmentation. Okay. As you go from here, there, the task becomes more difficult. Okay. So I'm going to introduce some of the architectures for performance. Any questions? Everyone know these tasks? Classification, detection, and segmentation. So the first architecture or network for doing classification was this network or architecture called LINET by Yakun in 1998. So this was probably the first architecture or network for classifying the input as one of 10 characters. The character that's written here is A, but this architecture really did digit classification. So handwritten digit, okay, in grayscale, or not grayscale, black and white. So the digit is written in black. And you want to classify, so the output is 10 outputs, and each one would give you sort of the probability of being a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And this probability, if you add up all the probability, would equal to 1. So softmax rate. So the way this works, it took a 32 by 32 image, and then it performed convolution, a 3 by 3, was it 3 by 3? 5 by 5 filter. 5 by 5. When I just write, people just write it like this, 5 by 5 filter. But you're actually doing this. This is usually left out. This is 3, so this is one channel. So there's no channel here. So it's a 5 by 5. And how many of these 5 by 5 filters do we have? How many? There are 6. Okay. We had 6 5 by 5 filters. And each of the outputs of each of the filters are drawn here in this box. Okay? And this 32 by 32 image became a 28 by 28. How's that? So there's this famous, not famous. So the way you would do this is, let's say this is n by n, and the filter is f by f, then it's n minus f, then you divide by this thing called stride, plus 1. So 32, so it will be 32 minus 5, that's 27, and the stride of 1. So I think in the last lecture, stride was defined, or convolution was defined. If you don't know this, everyone understand what stride is? Right? Right?
Can you explain what stride is?
Stride, okay, so I had a picture, okay, so it's, let's say, let's do something like this, okay? And you have a 2 by 2 filter. So it's 1, 2, let's say 1, 2, 4, 5, 6. These are the values. Some number, some number, some number, some number. Okay? So let's assume that I have here a 5 by 5 image, n equals 5 by 5 image, and I have a 2 by 2 filter, and I'm going to draw this blue. So I'm going to do convolution. And the way you do your convolution is overlay this filter on top of here. Let's say this is 1, minus 1, 1, 1, like that. So the first value right here, the value that you get, is you do an inner dot product with this filter and this region right here. So it's 1 plus 1 times, let's put this one. 1, 2, 4, 5, multiplication. One here, one here, one here, and one here to represent each of the filters, and so what do I get? This is 1, 2, 4, and minus 5, so I put a 2 there, right?
A stride is where do you put your, where is the next operation going to come? So stride of 1 means that the filter is going to be right over here, shifted by 1. Stride of 2 will be right over here, like that. Okay? That's stride. What's the skip? So let's say I do stride. Choose green. Stride of 2. Then what I have is filter 1, oops, 1, 1, 1, minus 1. Because it's stride of 2, it will be 6, 7, 8, and 9. Right? So 21, 9, that will be 12. So 12 goes right there. Okay, everyone understand that? Stride, the skip. Okay? Now, the example that I gave is, okay, so stride of 2, so that will be right over here. The next one you cannot do because you don't have anything. But you have this thing called padding. What do you do in padding? You put a 0 around on here. Okay. Then you may start doing so that it fits. The filter fits. So you cannot have filters sticking out. Okay. Anyways, that's stride. So the size of the image, the size of, okay, so we started with a 32 by 32. 32 by 32, so n is 32. The filter is 5 by 5. Stride of 1 plus 1 gives you what? 28. That's the value. That will be the size. So that's convolution. Okay. So you're looking at the local region to see whether the filter pattern is, how much of that filter pattern is in the image locally. You understand what I'm saying? What do I mean by filter pattern? So in this one, the filter pattern would be look like this. And something. How much of this pattern is locally on each region? That's what you get right here. Okay? And you have how many patterns? 6 different patterns. Okay, everyone understand that? And then you go, it's written as subsampling here, but we call it, what do we call it now? Pooling. And pooling is an operation that reduces the dimension. So a pooling would be, if I had a 2 by 2, then I'll be looking at this. If I'm doing max pooling, then what is the maximum value here? 5. So these 4 will be represented by 5. Then you shift. Then you look and look at the maximum value. Okay? So 2 by 2, and then you look at here, what's the maximum value? It will be 9. Okay. So if I do a 2 by 2 pooling, what's the size? It's been reduced to a half. But the channel size remains the same. Okay? You do the pooling on the image region. Then you go here, and then you do convolution. Okay? So going from 14 to 14 by 14, 6, and how do you get 10 by 10? What is the filter size? 5? So 14 minus 5, and what's the stride? 1, which gives you 10. How many of those? Oh, and how many of those do you have? How many? 5? We say 5 by 5, but actually by 6. Okay? So you have a filter that looks at 5 by 5 and all of this. You understand? Looking at all the depth. 6. 5 by 5 by 6. Now so 14 minus 10, that's 9. Stride of 1 plus 1 gives you 10. And how many filters do you have of those? 16 number of. Everyone follow this? And then, what happened? Self-sampling. Or sort of max pooling. Okay? So it has, this one has 2 convolutional layers. Okay? Each of the convolution layers are followed by max pooling. Okay? And then this thing is going through 2 layers of fully connected layers. Fully connected. So F represents fully connected. So this becomes 120. How do I get 16 by 5 by? So what is the size of this? 25 times 16 is what? 400. 400. Is that right? 400. Okay. And that has been, each one is connected and gives you 120. Fully connected layer means that this one node right here is connected to everything here. Well, you know, it's converted into 120, and then it's reduced to 84, and then it's to 10. Okay? And of course, I forgot the nonlinear operation. So it does a convolution, and then it does a nonlinear operation. And at that time, 1998, ReLU did not exist, or ReLU existed but it wasn't used. This one was the first one. Yes. And this was by Yakun. Okay, yes?
I have a question about C5 layers number. Why is 120?
Well, they just defined the output layer to be 120.
Why?
I think they tried various things. It's like saying, why 5 by 5? Why 28? Why 5 by 5 filter? Why did you use a 5 by 5 filter? Why? If you understood everything, why did they use 5 by 5 filter? They probably tried many different things, and 5 by 5 probably worked. It's 120 and 84 and then 10. But that's not really important. It's not really important because there are probably many ways to go from here to 10. And I'm going to show you another architecture that does it differently. Okay? People can read this. And there's this thing called normalization, which is not used. So each of these things might have values that are really big and small. So there is some normalization that's conducted, but people have found that that normalization really does not help. But anyways, so this was the first one. I don't want to, spend time. So zip codes, digits. We put digits here, and to recognize each one. This one's the first one by Jan LeCun. Okay, and he's right now in charge of Facebook. And he's also a professor at NYU. So people can look at that. Then the next famous one is this thing called AlexNet. Okay. And AlexNet, so Jan LeCun's LeNet had how many convolutional layers? No, actually two convolutional layers. And these are all fully connected layers. How many convolutional layers did this AlexNet have? 1, 2, 3, 4, 5. 5 convolutional layers and 3 fully connected layers. Okay? And here, it took, actually this is 227. I don't know why they put 2. It's actually 227. 227 by 227. Okay? 227 by 227. And it has what? It starts out with... No. What is this right here? It's 27 by 27 actually. It's not 20. And what's that? RGB. Red, green, and blue. 3 channels. It started out with that. Okay? And then this had used what's the size of the filter? 11 by 11. Okay? And so, what is it? And let's see. 227 divide minus 11 by 11, and I need to get 55. Plus 1 is equal to 55. So what is the stride? What is the stride? 4. And here it is. Okay? So people tired. I'm bored with this because I know all this. Who are seeing this thing for the first time? Oh, okay, that's good. Then you should be bored. Okay, now, you can see from this architecture, there are two chunks, here and here. Why do you think there's two chunks? At that time, they didn't have a GPU with high memory capacity. So they split it up. And how many filters? 11 by 11, how many filters? 48. 48. So 96 filters. So one GPU worked with 48 of them. Another GPU worked with 48 of them. So 96 of them. Okay? And then there's max pooling. So, what was it? It's 5 by 5. So this 5 by 5 became 27. So it's 55. Reduced down to I'm almost certain that it was max pooling by 2 by 2. Okay, the size was reduced to half. Okay. And then the next 5 by 5, and then it turned into 256 channels, 250 channels with 5 by 5, okay, and so forth. And this was proposed 2012, and it did much better than any other. So there was this competition. It's called ImageNet recognition. I forget what this is. There was this competition, okay, and it performed much better than the others. Okay, the top 5 arrow was 60%. Compared to the runner-up of 26. And he released this code, AlexNet, okay? And I think this is when deep learning really took off because there were code available. Okay, a lot of people just took this code and modified it. Okay. And the person who designed this code was, his name was Alex. Who's Alex here? You're Alex? Okay, you're Alex. But his last name was Krzyzewski. And he was a postdoc at Hinton's lab in Toronto. There's Professor Hinton. Yeah, so that's history. And here, ReLU was used. So after you do your convolution, for each data point, you do nonlinear. ReLU. You've heard about ReLU, right? So the way the works is this. You do convolution. So here, image, convolution with a filter, then you add a bias, and then this was sent to a nonlinear operation or sigmoid at this time. well, not sigmoid here, it's ReLU. And the ReLU function look like this. ReLU look like this. This is ReLU. Rectified linear unit. Oh. Rectified linear unit. So this is ReLU x. This is the value of x. This is okay. And it had some other things, dropout and local response normalization and so forth. This is not a course on deep learning. If you want to learn this thing step by step, there are many, many self-learning videos. Okay, so I just want to go over this because this is machine learning course. Okay, so yes,
Can I ask you about spooling layer? About spooling layer.
pulling layer, yes.
How did they get 128 out of 46?
Yes.
This bias.
So this is channels. So the way he's drawn this, it's convolution. How many filters did it have? 256. So he combined pooling and convolution in this figure. Okay? So this is not 90, so this is 96 convolutional filters. This is 256 convolutional filters. Okay? The way he's drawn it a little bit differently. Okay, so this is the Pooler image classification. Then in 2015, okay, by the way, this is where you can find the reference. It's a conference called NIPS. And there's another conference called ICLR in 2015. VGG, it's another very famous network. And here you are doing, okay, so you take a 200 by 20, 224 by 3 channels, okay, or 227 by 3 channel RGB image, okay, and you produce a 64 channel. So you have a 64 filters, and what is the size? What is the size of the filter? From here to here, the size did not change. And what's the stride? One. Stride is 1. Here it is. 3 by 3 and stride of 2. Oh, no. 3 by, okay, it's 3 by 3, so what is it? 224 minus 3, stride of 1 plus 1. How do you get this? Pardon? Maybe 0 padding. There you go, 0 padding, okay, maybe 0 padding. Then, okay, 0 padding, then you add 2, so it's 226, then a stride of 1, plus 1 is 224. Okay, good. So 0 padding, very good. And then in this architecture, it's 3 by 3, a stride of 1, and it does pooling, 2 by 2 pooling. So the size of the image is continually reduced. Okay. So this was a very high performing network. Okay. Was developed at Oxford University. By the way, okay, VGG, this AlexNet, the number of parameters here, how many parameters are there? Can you sort of guess? Do you think it's hundreds, thousands, 10,000, 100,000, million? Just give me a ballpark figure. How many parameters do you think there are? 50. No. 60 million. 60 million parameters. That's a lot of parameters. Okay? So this is VGG. People still use it. Okay. Now, this network, developed by Google, and in order to pay homage to the first network, which was what? No. LeNet. LeNet 5. So Google developed it to pay homage to LeNet. They named it this way. So, and here, the thing that's special is this thing called the inception module. And what is an inception module? So at each stage, you don't know whether to use a 3x3, 5x5, 7x7 filter. How would you know? It's difficult, right? Unless you perform all these experiments. So in the inception layer, why don't we try all of them? We have a 1x1, 3x3, 5x5 convolution layer. You have also max pooling layer. And it turns out the output are all what? 28 by 28 for this input size. 28 by 28. So different size filter led to same size with different strides, different same size size image, but with different channels. Okay? And what they did was they combined all of this. So adding 128, 192, 96, and 64 gives you what? 480. Very good. 480. They just concatenated. Okay. Now let's say I go to go. What is a 1x1 convolution? There's 1x1 convolution here, 1x1 convolution. What is a 1x1 convolution? 1x1, I left out something. What is the channel? 1x1 and the input channel, the size of the input channel. So what am I doing? So if I had, let's let's say I have three channels. Three channels like this, and I'm doing a one by one. Three channels. What I'm gonna get is, so let's say this is n by n. What I'm gonna get is an n by n for one channel. So what I'm gonna do is one by one means that value, that value, that value. I'm gonna take a linear combination of that. I'm gonna take a linear combination of that. So let's say this would be, usually people leave out, but there's a multiply by 3. If I had D, then this would, if it's D channels, then this will be D. Okay? So it's going through the depth, taking the linear combination of this. Okay, everyone understand that? And I may have many one by one. So I'm taking the convolution across the depth, across the channel. That's what one by one means. Okay? Same size, but I'm not going to have many, many. So in this picture, in the inception, let's say I started out with 28 by 28 by 256. And I have a one by one convolution, and I have 64 of them. What is the output? It's given here, but what is it? Let's say I have 50. What would this be? It's, let's say input is 28 by 28 by 256, okay? Going into one by one convolution, 50. What would be the output? Yes. It's the same size, and each one, there are 50 number of them. That's what it is. Okay? And you do this 28 by 28, 64. Same size. And then you do each one of them. Now, okay? Where here? Here? So I have a one by one, 256 filter, 64 of them. Does that make sense? 뭐가 이해가 안 되나? Well, let me just.
그 밑에 숫자를 그냥 마음대로 조정할 수 있다는.
그렇지, 마음대로. 그러니까 I can have as many. I can have 1,000. You see this? So this one by one, okay, one by one is looking at one pixel, locally, just one pixel. And then there's actually the D channels, right? Let's say D channels. So I'm going to take 3 times the first one, add 2 times the second one, plus 6 times the third one, right? Add that up, and that will be this value. I'm going to have another. And how many of this am I going to have? One by one. This one will be 1, 64. This one will multiply the first one by 3, 2, 1. This one would be 5, 4, 6. It's different filters. Do you understand what I'm saying? 무슨 말인지 알겠어? 그 64개 종류란 말이야. It's simple, right? So now, you see this inception layer, the idea of inception layer, I don't know which one to use. 1 to 1, 1 by 1, 3 by 3, 5 by 5. I don't know which one is good. So I'm going to use all of them. Okay? Because if you look at AlexNet, it had a particular one, 3 by, or VGT, they used a particular filter. So here I don't know. So I try all of them. Okay? That's the idea. Okay? But I want to combine them. It's going to turn out that the output is going to be the same size. But why is it going through 2 stages? Why is it going through this 1 by 1 and then going through this? Why is it going through this 2-stage? Here, I'm going this thing through very, very fast. I understand that, but it's sort of like hand waving. But I cannot go through this thing in a very systematic way, because otherwise we cannot do this. I mean, it will be just deep learning class, right? Why is it 2 stages like this? Why not just go from here to this output? No. The reason here is that if you go through this layer, so the channel was 256, yeah? So look, so for each output is 28 by 28 by 96, right? For each output you have to do 5 by 5 by some number of filters, right? If I didn't have this, and it worked out this 256, it would be a huge computation. Huge computation. So, in order to reduce that, it goes through this stage. And you can reduce the computation greatly. And so this GoogleNet, how many parameters by using, even though you have many filters in each one, how many filters? How many parameters? Only 5 million. How many did I say for AlexNet? 60. That's a reduction of 12. And what's the reason? Because of having this. We went through this stage. Okay? And it turned out, the math turned out very well. So you got 28 by 28, all of this same size. So you could just put it together. Okay? And you will see that. So it looks like a much more complicated network. Input. Much more complicated network. But because you see that inception layer right here? Inception layer, inception layer, inception layer, inception layer, inception, many inception layers. Huh? It seems like more, but the parameters by 12. The only thing that's unique here, right, all beta inception layers, there are these things blue, written by this blue thing. Intermediately, it's doing not only back propagation from top to down here, but in the intermediate layers. Because it wasn't doing gradient descent, propagating the gradient very well. You know, the gradients, as it goes down here, if I didn't have this, the gradient will go small, small, small. And I cannot learn this thing. So I'm pumping in, I'm doing back propagation just down here, and propagating down here this way. Okay? So I can update this. And I'm doing this thing really fast, but don't criticize me because, this is. Then there's this thing called ResNet. Okay? ResNet has a structure that looks like this. It goes input, usually it's convolution, and goes up, right? It has this choo, identity layer. Okay? Why does it have this? ResNet is characterized by this identity layer. Why do you think? What would help with this? When you do backpropagation, I don't have, as I go through each of the layers, I have to, there is a nonlinear unit right here, right? If I take the derivative of the nonlinear units, the gradient is going to go down. And it's, in order to update the parameters down here, the gradient has to be sort of significant, right, for it to change. If I have this layer, I'm skipping all that. So the gradient is passed down much in much better way. So you can see that with ResNet, there's 50, there's ResNet 152 or something like that. You can see that there's skip. There's skip. Okay? And this one tends to perform better than any others. Okay? Ooh, what is that? Now it seems like inception, multiple. This is, you can sort of skip this. Okay. This is a sort of like 2017. Now I want to go and talk about detection. Okay. Please ask questions. So, what was the task of detection? To find the location of the objects that you have already predefined. So usually there are maybe 200 objects that you about 200 objects that you would like to find in the image. By the way, the ImageNet, competition that I mentioned, AlexNet did well, VGG did much better, Inception layer did much better, Google.net did much better. There are about 1 million training image. 1 million. So I was hoping that you would collect about 1 million data set. 1 million collecting 1 million. Think about it. That's a lot of work. That's a lot of work. Okay. 1 million image and 1,000 classes. 1,000 things that you want to class. Okay? And I mentioned top 5. So what is top 5? Meaning that each network would say, would give you get an image, and it says, oh, I think it's going to be 1, 2. It's going to be either 1, 2, 3, 4, and 5. That's top 5. Huh? And if it's in there, then you get it correct. That's top 5. Top 5 right now, I think state of the art is maybe error rate of 3.2. It's probably below 3.2, something like that. Okay. But top 1 is much higher. There it is. The error. So I mentioned that. Now detection. Here about 200 classes, and I want to find out where they are. That's image object detection. Okay? And the first one that was really significant is this RCNN. Okay? That was post 2014. So here's an image, and search algorithm, through some search algorithm, I'll explain a little bit later, it tells you, oh, I think the objects will be here. I think the objects will be here. And it gives you these boxes. And here, what you do is, you take all these boxes, RCNN, so these regions where the boxes, and then you put all these boxes and standardize them to fixed size. Fixed size. Okay? So here it is. You take about 2,000 for each image, possibility of objects being there, 2,000 of them, through this algorithm called selective search algorithm. And then each box is standardized to a certain size box. And each box is sent through a CNN. And what do you get out at the CNN? The feature. This is also very, very important, and I didn't mention this. This is very, very important. Very, very important. This and also this. Very, very important. Look, this is, you have an image. This is for all. Image comes in, and it's probably going to go through some convolutional layers, many convolutional or inception layers, whatever. At the final layer, you usually have a softmax, okay, giving you the probability of each of the objects. Okay, so if there are 1,000 objects, then probability of each one being what probability, and then when you add them, right before is the feature that we can use. Feature representation of this. And maybe you can use this feature, you can use this feature. It's sort of the X's that we usually say. The X. And then we have to put a label on this, Y. Okay? So, deep learning gives you features. That feature you add on with a softmax to be used for classification. Okay? So the last one is a classifier. All these are features. Okay? So deep learning gives you features, okay, for performing good, for performing high accurate classification. Okay, that's a very important message that I want to send to you. So what is this? This CNN takes each of the boxes and gives you a feature. And based on this feature, this is the X, you send it through a classifier that we're going to learn, the support vector machine, to see if each of the box is an object that we are considering, or an object not considering. So what kind of classification is that? Binary classification. So for each box, is that the object that we're looking for or not? So each 2,000 of them, you resize it. And then you get the feature inside here. And is it, object that we want? Or you could send through each one of them object classification. Oh, here it is, object classification. So you can detect objects. So this is, object classification, sorry. Then there's this thing called fast RCN. Okay? Here, the new concept is, okay, I'm sorry to mention. So what is selective search algorithm? How do I get this box? Without going a lot of detail, is clustering. And then merging. And then you get big chunks. Image into big chunks. Okay? But it's a little bit more complicated. Anyways, so that's how the region, oh, I think there's objects here. That's how the regions are proposed. 2000. In fast RCNN, you get rid of this selective search algorithm. You have a concept called ROI, region of interest. It's proposing, well, oh, it's telling you, oh, this might be interesting. This might be interesting. Regions. Okay, you have a network for getting the regions. Okay? And then you, here, you do, is it object or not? And you may want to modify the box. Okay? Then came faster RCNN. These are like landmark papers. So you have an image that's going through this feature. It's giving you a feature. It's a representation of this image feature. And then it has something called the Region Proposal Network. We call it RPN network. And this network will suggest to you where the image might be. RPN sort of suggests to you where the object might be. And then, if you know where it might be, you take the feature corresponding to these regions, ROI regions. These are called ROI regions. And then you do classification based on these features. Okay. One more, two more. Okay, two more. Okay. Now, actual implementation of this. There's this concept of anchor. So what happens is, you take in the feature map, you have uniformly spaced points, okay? And you have these anchor boxes, okay? It's a region where you're going to do, you want to find out where there's an object. So the anchor boxes would have different scale, so it's maybe 128 by 128, 256 by 256, 512 by 512, okay, square boxes, but and with different aspect ratios, okay, boxes around these points, okay. So around uniformly spaced, you look at the box around here. 256 convolutional dimensional layers. And from this, you do, so for each point here, let's say for each point, let's say each of the points that we're going to look, each of the points are going to have, you have a one by one convolutional layer that tells you whether there is an object or no object. And also, it has sort of a modification of the boxes, giving you updated prediction or the shift of the center point, X and Y, width and height coordinates. Okay, so you have convolutional for each of these points here. You have saying whether it's an object or not object, and you have modification of this box, where the center box is. Okay. Okay. So that's how it's. That's where it is right now. And now I want to talk about segmentation. Okay, so I talked about detection. Now segmentation. This network, UNet, okay, because the network, the architecture was shaped like a U. Okay. It's illustrated in a U manner. And this is a segmentation algorithm that did very, very well on bioimages in segmenting cells. Okay. This is output is binary. Yes, the cell is. The output, if you look at here, it says two, it's binary. Is that foreground or background? Okay, it output foreground and background. And what's unique about this, see that for different database, comparing with others, this one had very high accuracy. Okay, and what's different about this compared to other database is that the data was very, very small. There weren't a lot of data. So for very small amount of training data, and the way this architecture works, it takes an image and reduces the size. Okay? It reduces the size, and then after reducing the size, it upscales. Okay? But what's unique about this is that there is connection. The first layer, the beginning layer, is connected to the last layer. The mid layer is connected to the mid layer of the upscale. And so forth. There's some connections here. So as you're doing backpropagation, you're not only backpropagating this way, you're backpropagating this way as well. This red, by the way, means downscale by a factor of 2, I think. Okay. And this one is upscaling. It's written right here. Upscaling. So the way the original people who proposed this, I think the people who proposed this are from Germany. As you downscale, you reduce the problem of where, because if you have a big image, you have to, you have to have information of where the objects are, or the cell bodies are. But as you downscale, the problem of location has been reduced as you go down here. Anyways, there are references that you can read, and there are good videos representing each one. So that's a very quick overview of the task and some significant architectures that you can study on your own. So I stop here. Any questions?